Welcome to week 7 of Math 20. 2 questions to start with today. One is about how area is always square units. So I'm going to take this picture from the lecture that we used before just to make sure we understood the formulas and put it in the Jamboard. And I should write what I'm doing. Okay, so the idea is that if I want to talk about area, I have to be able to do it in a meaningful way. I can't just say things are like big or small, that's too vague. So I need something to be the official unit of how big things are. And so the thing that works best, and remember again how we started with rectangles and folded paper and got everything else based on rectangles, was bits of squares, because it's easy to take rectangles and break them up into squares. So in this first picture with the red triangle, there's 12 squares, 4 and 3 make 12. And if I'm wondering how big this rectangle is, then I'm going to start, that's kind of faint. Let's pick a better color. There we go. I'm going to start, no, there we go. Coloring in a square. So there's 1 square, 2 squares, 3 squares. And this one I'm missing a little bit. So let's put this little kind of corresponding missing bit with it, right? So now we have 3 squares shaded. And here, that's like part of a square, but this part corresponds to here. So now I'm up to 4 squares. This one's entirely inside, 5. And this one is missing a little bit on the outside, but that matches here, so 6. So we get 6 squares that we've shaded in. And in other shapes, it won't work out so nicely where this piece that was missing from here will also match what's happening there. We're not going to get these nice exact squares by cutting and pasting with scissors. But the theme is the same, that even if I can't say this part fills up a square and we get an entire square, that's our goal. Our goal is to paint squares. And so it makes sense to count area in squares. And we'll get a decimal answer or a fractional answer sometimes. It's not always a whole number. But in the back of our mind, then sort of imagine you have some little person with a paintbrush who is painting the squares as you go. So that's why the answer is always in square inches or square centimeters or square feet, because we're literally shading in squares one at a time as we go. Does that make sense?
Yeah.
Okay. On a totally different note, this one isn't about the geometry. This was a unit analysis problem. Someone asked about turn-in homework number 5. So in case you don't know, Amazon has not only the one that we normally see when we search for Amazon, but there's the UK version also. Was it this class I talked about Tor for the web browser? Tor?
That doesn't sound familiar.
Okay, there's an interesting tangent about this if you want another time. Anyway, so if you go to the amazon.co.uk, you get the British Amazon where everything is in pounds and grams instead of dollars and ounces. And the prices aren't the same because Amazon changes prices based on local demand. If you were taking another tangent in my Math 25 class, then one thing you would talk about on Tuesday of this week is that Amazon has been known to even adjust their prices during the day. So compared to the Sears website, where starting at 12 midnight, everything stays the same price all day long, then Best Buy and Amazon will have some wiggles. When people get home at 5 at night, the prices at Best Buy increase. And then they get down to the kind of the normal price after dinner time, so that everyone that shops during those hours is paying more for shopping at that convenient time. And then Amazon, product by product, will have things wiggle all over. They're much more volatile. So anyway, you don't care about that. So it's no surprise that at one point in history, when I looked at the prices for something, I used Sculpey modeling clay because I figured that was exactly the same no matter where you bought it and easy to ship, that the prices don't quite match. So if you were to shop at the two different places, which is a better price? We have to compare dollars and pounds. So that I give you an exchange rate, which is no longer historically true, but was then. And we have to go between ounces and grams. So here's the conversion rate for that. So if we're going to compare them, we need them to be the same. We could take the dollars and ounces and change it into the British rate, have them both be pounds per gram. Or we could take the British rate and change it to be dollars per ounce, which I'm guessing will feel more natural to everyone here. So let's do that second plan. Let's take this rate and change it to be dollars per ounce. So just to rewrite what we're doing, we're saying that 2.2 pounds for 57 grams is how many dollars per ounce? Everyone okay with my goal?
Yep.
So using the unit analysis, I take what I start with, I write it as a fraction. In this case, it already is. And there's two things I need to change. I need to get out of pounds. So the pounds will cancel. And I need to get out of grams. So the grams will cancel. And we've done this a bunch. If something starts out on top, then I put it on bottom. So there's one on each top and bottom, and they'll cancel. When something starts on the bottom, I put my new one on the top. So again, we have one top and one bottom, and they can cancel. Okay, grams turns into ounces. And looking over here, 1 ounce is 28.35 grams. Pounds turns into dollars. And at the time, 1 pound was $1.31. Everyone okay with my setup?
Yep.
What's my next step?
Multiply across.
Multiply across. So we have 2.2 times 1.31 times 28.35 and 57 with times 1 times 1. On top, all that's left is dollars. That's what I want. On the bottom, all that's left is ounces. That's what I want. Finally, any fraction, I'll make a number. If I had room on my slide, I would write 2 steps, but I'm just going to multiply the top 3 and then divide by the bottom, and be a little rude with my lecturing that I'm not putting every single step separate, but that's okay. So I'm not quite done. Here we have $7 and change for 8 ounces. Here we have a little more than $1 for every ounce. Which one is going to be cheaper? The one that's less than $1 per ounce, right? If I wanted, I could multiply by 8 ounces here and get 1147. That day in history, Sculpey was quite a bit more expensive in the UK than here.
All right, so I have another question, and I'm gonna try to state it as clearly as I can. So sometimes in these word problems, we have I don't know how to word it. Sometimes when we're starting the fraction at the beginning, we put it over 1, but we don't label the bottom.
Right.
Correct? And we're not labeling the bottom because we're using the label later on in the problem so that we have the label in the correct spot. Does that make sense? Am I making any sense?
Let's pick one that was like that and see. So the first day we did unit analysis. We did 5.7 inches is how many feet? So this was way back in your notes. So in this case, 5.7 inches is not a rate. It's just one number. There's nothing that it's being compared to, which is very different than, whoops, that one.
Correct, yeah.
This one here is a rate. It is a comparison that we have so many pounds per gram. So since this one already started as a fraction, because rates we write as fractions, then I could just put it there. I don't have to do anything to it. Whereas this one isn't a fraction, it's just a number, how long something is. So to make it a fraction, I have to put it over 1.
Okay.
And I'm not putting it over 1 of anything. It's not per 1 day. It's not per 1 pound. It's just over a plain 1. If I put it over 1 something, I would be changing it.
Right, and then you don't have the something later on in the problem where you need it in the correct spot. That's what I was messing up with on my homework over the weekend, and I realized as I went back into my notes. And so I guess that was, you answered my question right away, was we put it over 1 because it's not already a fraction. It's not, we're not comparing it. We're just trying to find the rate of something else.
Right. Now all the fractions we add later replace either the top or the bottom unit. Right? The blue fraction replaced pounds with dollars. The green fraction replaced grams with ounces. If I don't have anything in the bottom, if it's just 57 inches, then not only does this not get replaced, but I can't create something that goes there. And that means my answer will also not have anything in the bottom. I'm turning 5.7 inches into how many feet? And it's just feet. It's not feet per day. It's not feet per hour. Right? It's just a plain thing. So this will always be true. If something starts out as only a number, not a rate, we can only change it into something that's a number, because we can't add or destroy how many units there are. On the other hand, if something starts out a rate, the answer will also be a rate, because I can only replace units. I can't get rid of them or make more of them.
Got it. Thank you. That's more clear for me now. Yeah. Thank you.
You're welcome. Anyone else have questions or comments about that dynamic? Okay. If it helps, remember back from lectures a while ago, we had this thing that was awkward and not used really called the goes with chains, where we would take rates and smash them together in a weird way. That was the primitive way to do unit analysis. It did not work as well. So we stopped doing it. The reason we did that briefly, even though it was primitive and quickly obsolete, was to try and get in your head that when you have a rate, you can smash it together with other rates. And that's really all we do with rates. We don't add them, we don't subtract them, right? All we do is sort of figure out how they fit together, which rates go with other rates. And we do that with either this bad process or with this better process. So when you see a rate in real life, when people are wondering in the news how many people are voting per day in the local election, or how many cases per day of a disease are happening in Florida, or whatever you're reading, then when you see a rate, think that, the only thing I really can do is see what other rates it goes with. We don't do other arithmetics with rates. Unlike when you have a plain number and someone says, I know how much I weigh today. Maybe I'm wondering how much I'll weigh in a week, or maybe I'm wondering how much more than my kid I weigh, or maybe I'm wondering what percent change did I have from my last doctor's appointment, or something like that. There's lots of arithmetic we do with plain numbers that we just don't do with rates. Okay.
Thank you. I appreciate all that. Yeah, that helped settle it in my brain a little bit more. Thank you.
You're welcome. Okay, any other things about mad science at all? We're done with mad science, so it's just your questions, probably on the turn-in homework.
I'm still having problems, but I'm pretty sure that you and I were gonna meet up tomorrow. Right?
Well, and Caitlin, you're doing your first time you talk is too quiet once again.
Every time. Can you hear me? Can you hear me?
Vaguely, go ahead.
Can you hear me? Sorry, I don't know what's up with the speaker on this thing. I was just saying that I'm still confused, but I was pretty sure that you and I were gonna talk about that tomorrow.
Well, you're not the only one confused, so if it's just a question on the board, go ahead and ask it.
It's not so much a question on the board as it is a couple different aspects of mad science.
Okay, then we'll save that for next time.
Okay.
Anyone else? I'm happy to do more review before we go on to the justice topic.
Can we do like 9 or 10?
Sure. They are very different because one is polygons and the other is circles, but they are all just formulas. So I'm actually going to do this two ways. So let me go there and paste it again. Okay, so some people don't mind looking up in their notes the trapezoid formula. So if you know that, then when you have a trapezoid, base 25, top 16, Height 35. Oh, so I drew mine wrong. This is much taller than it is. Still not to scale. That's okay. You are not grading me on my artwork, so. So if you have the formula, then the area of a trapezoid is going to be top plus bottom divided by 2 times the height. It was the average of the top and bottom multiplied by the height. Okay, so 16 plus 25, then divided by 2, then times 35. I'm getting 717.5 square centimeters. And if you wanted to write it as centimeters with a little exponent, good for you. So that's sort of the quick and easy way to do this. I don't mind having a formula for trapezoids, even though I will probably never use it in real life.
So
I
for
put
some
it in
reason
my notes.
I had in my notes, I had, it was top and bottom times height divided by 2. That's not right, huh?
It doesn't
That's-
matter. You can do those two in either order.
Oh, it doesn't matter?
No.
Oh, so for my answer that I got for my homework, though, I didn't get a decimal. I just got 7,175 square inches.
I'm not sure why you'd have a times 10 bigger. Did I do it wrong?
I don't know. Maybe I did it wrong. I'm going to check.
I think I did it right. Other people's calculators match what I did?
Oh, yeah, I do have a decimal. Yeah.
Oh, okay.
I probably just, yeah, okay. All right, so it doesn't matter where we do the divided part or the divided
No,
by
as
2
long
part?
as you have the parentheses so that this is one thing.
Right. Because then I had 41 times 35 divided by 2, and that was the equation that I put into my calculator.
Yep.
Okay.
So what happens if you're stranded on a desert island and for some reason you have to do this and you don't remember your trapezoid formula? Then the thing to do is chop it in 2. You can always make a diagonal, and now we have an upper triangle and a lower triangle. So for the top one, the area of a triangle is 1/2 times base times height. Can I just do base times height divided by 2? So for this one, the base is the 16, the height is the 35, and that might not be terribly obvious, but imagine that we're taking a mirror and kind of putting it here to flip it over. So this is the base, and how high up does it go? It goes up the same height as here to that point. Does that make sense? Or maybe you could imagine moving to the other side of the paper. It's going to look like that once we flip it. Whoops, not the 1635. And then for the yellow one, oops, I never actually finished with blue, did I? One moment, I'll go back and finish blue. Oh, okay. And then when you're done, you add them together. So I do this for two reasons. I don't expect anyone to actually do it this way when we take our test at the end of the term. Since it's an open notes test, I think everyone will just have the formula, plug things in and get the answer and be happy. But I wanted to point out that we have the top contributing and we have the bottom contributing. So here is where the top contributed. It was actually the base of the blue triangle. And here's where the bottom contributed. It was the base of the yellow triangle. So maybe that helps you understand the formula better for when you do use it the only time in your life on the test at the end of the term. Okay, questions about either slide?
On that first slide, I can't see the times number. I'm assuming it's 35
Yes.
because the pictures are in the way there. But so it's 16 plus 25 divided by 2
Mm-hmm.
and then times 35.
Yes. And you have to put the parentheses in. Otherwise, the divided by 2 is only going to happen to the 25.
Right.
And you'll be bigger by 8 because the 16 won't get divided by 2.
That's what I was missing. Thank you.
And you'll have that extra bigger by 8. And when you multiply it by 35, you'll be bigger by 8 times 35. Okay, everyone happy, especially with this slide, which I expect is how you will really do it?
Yep.
Yes.
Okay, then number 10. I'm forgetting these are your turn-in problems, so this one I'm going to change the number so I don't give it away too much. Let's pretend you have an extra big backyard trampoline with 18 feet. So in other words, is the diameter all the way across or the starting at the middle distance?
Diameter's all the way across.
All the way across. So that one is 18. If I happen to want the radius, then how big would that be?
9 feet.
9 feet, because it's just halfway of all the way across. Everyone okay with my picture?
Yep.
So area of a circle is pi times radius times radius. If you liked radius squared, you could. So in this case, I want the 9. So it's about 254 square feet. Your problem that really starts with 14 feet would have a smaller number than that.
And square feet, it can have the decimal, or is it better to round up?
You could certainly have a decimal. I didn't want to include it just because of the situation. How accurate do I think trampolines are really manufactured? Are we measuring just the fabric or the spring and the outside part also? There's enough vagueness in the real life situation that saying it's 0.4 or 0.5 seems silly. But if you like the decimal, you can keep it there. Okay, so let's move on. That was good review. Now we're starting the new topic where we have equal signs that really matter as equal signs. So far in class, we've had equal signs, but usually we thought about them as it's the next step in a process. We don't really think about it each time that this thing equals the area, and this thing also equals the area, and this thing also equals the area. That's true, but mentally we're probably thinking that these equal signs means I'm moving on to the next step of the solution. I'm not really saying two things are equal, even though they are. So we've had lots of equal signs, right? These things equal this, but it's still mostly that mentally these equal signs to us mean it's the next step. So now we really care that the equal signs means things are equals. So I'm going to start by talking in review about equations you can solve in one step. If you're in the free online textbook, there's a few places based on if you have decimals and fractions or not. Some as early as page 16 and some later in chapter 3 with page 259 and 268. If you're in the green book with zebras, again, it's sort of all over the book because they do this sometimes with whole numbers and sometimes with decimals and sometimes with fractions. And that's okay. And as usual, when we start a topic that is a review topic, then I'm going to use pictures because that helps some people. And if the pictures don't help you, then feel free to ignore it. But we should talk about how these work. So let's start here, just with the simplest review. Let me get one that. Okay, so we've seen these kinds of things before, probably. I have 5 times a letter, 35. It's 35. I can actually write what I'm saying. Okay. So I want to know what goes in here. Traditionally, we write a letter, but if it helps you, you can just imagine, as it's sometimes written in elementary school, that this is just a box to fill in. And we could put in different numbers. Does 5 times 5 work? No, that would be 25. Does 5 times 6 work? No, that would be 30. Does 5 times 7 work? Yes, 7 is our answer. But in order to manipulate more complicated things, instead of a blank box, we're going to use letters. And what did we actually do when we were doing the guess and check? We were saying that something is being multiplied by 5. So we want to think about what that thing might be. And to think about it by itself, we want to do the opposite of multiply by 5 to kind of get it back to where it was before we disturbed it. And the way to undo a times 5 is divided by 5. We've been told that if we do something to one side of an equation, we have to do it to the other. So we get y times 5 divided by 5 is just back to y. And then 35 divided by 5 is 7. Okay, everyone okay with number 1 on the board? You've seen things like that before, or if not, you're doing okay.
Yes. Thank
Everyone
you.
is quiet. Okay. So let me try and fill in what maybe you've seen or maybe you haven't. So if we want to solve 4 times b equals 20, I could do the same thing I just did. I need to get b by itself. The opposite of times 4 is divided by 4. So b times 4 divided by 4 is back to just b. 20 divided by 4 is 5, and I know the answer is 5. So when we said the yellow divided by 4s are important because we're doing the same thing to both sides of the equation, then how can I explain that in a picture if I'm someone that likes pictures? The picture has 4 b's, and they weigh as much as something that weighs 20. So where is the dividing by 4 happening in my picture? Okay, one moment. I'm going to pause the recording and tell my boys to be more quiet because they will get louder and louder if I don't. Okay, back to us. So where's the divided by 4?
I don't know. I don't get that.
Under the 20?
I can take the 20 and chop it into 4. So now I have 4 rectangles on one side and 4 rectangles on the other side. The divided by 4 would be I'm going to, that's kind of thin. I'm going to get rid of most of them. I just have 1 of the 4 rectangles on each side. Oops, I need to pause again. One moment. Okay, sorry about that. My screen went dim, which made me think I forgot to plug in. So here we are. Okay, so I did a divided by 4 just to say on each side, I only care about 1 of the 4 pieces because that's 1b. And then how much does 1 of those 4 pieces weigh? That's just going to be 5 out of the 20 because 5 4s make 20. So as I prefaced before, maybe this helps you, maybe it doesn't. If it does, great. If not, just move on. What we want you to do on your paper is this part. Just solve the equations in the way you may have seen before. If it helps you understand why it works, then the picture is good, but no one is going to draw pictures of scales to solve these problems.
And each side of the equation that we're working on is the letter plus whatever, and then equals is dividing the two.
I think I understand what you're saying. The left side of the equation is the left balance weight. The right side of the equation is the right balance weight, because we're saying the two things are equal. What paper are we doing this on? We're just starting the very top of the justice. Is that what you're asking? Okay. So that was a multiplication. We did 2 ones with multiply. Again, the important thing is that you can manipulate the numbers on the paper like this, but if the picture helps you understand what you're doing, then great. Now let's move on a little bit. The next thing to do is divide. Whoops, there we go, divide. So again, what we really care about is if you had p divided by 6 equals 8, I can say what's the opposite of divided by 6? It would be times 6. Then if I have p divided by 6 times 6, I'm back to where I started with p. 6 times 8 is 48. And I put a box around it because I'm done. So that's the part we want. The rest is just sort of fluff if it helps your brain. Here's a picture. Where is the times 6 happening? I forgot to grab that part.
Is it where the P is on the scale?
So here I have 1/6 of the pie or pizza or whatever it is shaded. And I've only shaded 1/6 of my whole thing called P. P is for pie or pizza, because I have P divided by 6. So this is just 1/6 of the whole P. Everyone see that?
Mm-hmm.
So if I did times 6 to it, that would be saying I don't just have one slice, I'm actually going to shade in all the slices. Now my pie is full. But if I made 6 copies of this slice, then I also need to make 6 copies over here, which will be an artistic challenge. So it was true in the beginning that my 1/6 of a pie was 8. Now I'm back up to my whole pie. I've restored it with times 6. And when I make this the whole thing, how much would it be? 8 and 8 and 8 and 8 and 8 and 8. So 6/8 is 48. So if the picture helps, great. If not, don't worry about it. As long as you can do this, you're in good shape. Questions about any of that stuff with balance scales and equations so far? No questions. Okay, then let's move on. One thing that will matter a whole lot if you're going into Math 60 is how you write things. We've seen already a few examples of how math, even though we might like to think of it as a mental activity, is very much a physical activity. How you put things on the page matters. How you press your calculator buttons matter. So if I want to do 3 times y equals 210, then, as you've seen all today, every time I do a new step, I'm going to move to a new line. What's the opposite of times 3? It's divided by 3. If I do it to one side, I have to do it to the other. And this is nice because what happens if I don't have a fancy thing with colors? Instead, I'm just writing with pencil. Or I'm an old-fashioned instructor teaching Math 60 on the whiteboard or chalkboard, and I only have one color of pen or chalk. You can follow what's happening. Here we have the original problem. Here we sort of have the action step. What are we doing to both sides? And then here we have the consequence of that action. And in Math 60, you'll have more steps than this. You won't be done in just one action and consequence step. So you'll do an action, there'll be a consequence. You'll do an action, there'll be a consequence, and that will keep repeating down the page. Just like with some of the things we've done here, then you have something, there's some original, there's some consequence, and we'll keep going. I can see what's happening, especially once I've done a bunch of these and I get used to this alternating action, consequence, going down the page. If I tried to do this all in one line, then I could say 3 times y equals 70. And what's the opposite of times 3? It's a divided by 3. And that gets y by itself. And whoops, I wrote this wrong. This isn't a 70, this is a 210. Sorry. Let me just start over as I'm narrating. I could say 3 times y is 210. What's the opposite of times 3? Divided by 3. That gets y by itself. 210 divided by 3 is 70. So the problem with that is it's blurring together the action and consequence steps. When I go back in week 10 and try and study for my final, I'm going to look at this and it's not clear what's the original problem, what's my action I'm doing to both sides. I just have to look at it longer to kind of decode what was happening back in that day when I did this problem the first time. Similarly, if I'm working with a neighbor, this is harder for my neighbor to look at and see what's happening each time. So you are very strongly encouraged to always write this style where the action and consequence take up their own line going down vertically. Don't try and squeeze the action step horizontally into the same row as you had already. The more complicated these get, the more this will be confusing. So that's what this is. Use the vertical format, not the horizontal format. Okay, let's do one just to scare you. That has a fraction in it. Oh no. Okay, try this one, and then I will do it when you're done. Okay, what action step am I going to use?
Divide by 8.
Divide by 8. Did anyone do divided by 2/3? It's a common thing to do. We're doing divided by 8 because we're trying to undo the times 8 on the y. The 2/3 is just sort of, who knows why it's 2/3? Somebody measured that. So that will indeed get y by itself. Y times 8 divided by 8 gets back to y. Now I want to do 2/3 divided by 8. The wrong thing to do, again, treating this as a physical activity of moving things around on paper, is to try and squeeze 2/3 divided by 8 into this little space. That breaks my flow. So I'll come off over to the side. I want to do 2/3 divided by 8. So that's going to be 2/3 divided by 8/1. So that's 2/3 times 1/8. And I can do some canceling. And I'm getting 1/12. Everyone get 1/12? Or if you didn't before, you did now. So a few comments. First, I can check my work. Is it really true that 1/12 times 8 is what we want? So yes, one nice thing about these problems is you can always double check things. Plug in your answer to the letter, and does it work? You can see if you got the right answer. A second comment is that by moving all of this blue stuff to the side, instead of trying to squeeze it in here, then we've kept the flow going very nicely. We can tell what's happening on each side of the equation quite clearly. I can share this work today with a friend. I can look back at it at the very end of class and see what's happening. So look at what you wrote on your paper and compare it to this. And you don't have to do it exactly the format I do, but whatever you do, try and make sure that it's really readable what's happening. Okay, any questions about number 5? I'll also say that I wrote like way too much in blue. If you wrote less than that and got 1/12, that's great. I am writing extra because I am lecturing. Everyone is suspiciously quiet. Should we go on? Are we okay?
I'm good to go on.
Okay.
I'm exactly as lost as I always am.
So we can also add and subtract. We've done multiplying and dividing, but there's nothing special about any one arithmetic operation. They all have opposites. I have u plus 9 is 200. What's the opposite of plus 9? Subtract 9. If I started at u on the number line and went bigger by 9 and less than 9, I'd get back to u. And then 200 minus 9 is going to be 191, and I'm done. Again, look at how you're writing things. Are your letters lining up? Are your equal signs lining up? Is everything sort of moving down the page in an organized way? If I had subtraction, it could be the same. What am I going to write as my action step?
You're gonna plus 9 and
Plus
then
9. Yeah.
they go over there and plus 9 with the 79.
So I had some amount of money. I misplaced $9. I found it again. I'm back to my original amount of money. And 79 plus 9 would be 88. Okay, questions about this whole process, what I'm calling one-step equations, because one action step gets you to the consequence you want, and we're done.
I missed the answer to the 4 plus 9 equals 200. Was it just 4 equals 151? Or 191, I mean.
Yeah, 191. That's a U, not a 4.
Oh, it's a U. Okay.
Yeah. I'm doing
That makes more sense.
U, V, W, X, Y, so if you did all of these on your paper, you can tell them apart better. So, yeah, U, not a 4. Good catch. Okay. We could be extra fancy. You're not going to see exponents, but you could do this. So if we have 9 is x squared, then what's x going to be?
9 equals x times x.
3.
3. And we might not be able to explain this quite as well. What I'm writing here doesn't look as nice, right? What I'm thinking is that what times itself is 9. And the answer is 3 times itself is 9. But that's different, right? That doesn't on the paper look at all the same as let's do an arithmetic operation that's the same on both sides of the equal sign. I would want to write, let's see, how do I do this? I'm going to go here. Okay, good enough. So square root it. Something like that, where I'm doing the same thing to both sides of the equation. But we don't have a nice thing to write there the way we do for +9 on both sides or -9 on both sides. So that's why we're not doing these, because it just doesn't look as nice. But it's exactly the same thinking of what am I doing on both sides. Something times itself is 9, something times itself is x squared. Let's undo that. Okay, enough of the confusing one. So what happens if we have 2 steps? And I'm going to show you the 2-step ones for 2 reasons. They're not in the book. Neither book, for some reason, trusts you to do this. I don't know why not. But there are some problems that look very, very similar to what we've been doing. And you try them and they don't work. So let's talk about that. Actually, I want all of this. So if I have y times 3 equals 9, or if I have 3 times y equals 9, oops, let me make that not in an alarming color. These are exactly the same. It doesn't matter which order I multiply things. I can say for both of these that the left-hand side of the equation is y times 3. I can go this direction with multiplying just as well as that direction. That's really important. In a moment, I'm going to use this as a tool. So for now, it's just an observation, but it's about to become a tool in our toolbox. When I'm multiplying, either order works. I can switch them. So for both of these, I just want to say, let's divide both sides by 3. And I get an answer. Everyone okay with a slide where things go smoothly? Okay, so oops. Now I have similar problems, but one of them has y divided by 3, and the other has 30 divided by y. So they're different problems. That's the first thing to notice. And the second is that the order is switched, which changes things with division, right? 8 divided by 2 is a whole number. 2 divided by 8 is not a whole number. So unlike multiplication, I can't just switch the order of things and not care about it. If I want to solve this problem, I can say, well, y times divided by 3 and then times 3 gets me back to y. And I could get y is 90. And you can check that that's true. If I plugged in 90, 90 divided by 3 would be 30. In this problem, if I just stare at it, what's y going to be? It's a different problem. It has a different answer.
Y is going to be 10.
10. I can see that 30 divided by 10 will be 3. But how do I get there? Because the order of division matters, I can't do a times 30 because I don't have this isn't that I started with y and then I divided it by 30, so I can do a times 30 to get back to y. This is the opposite. This is I started with 30. I have to start here. And I'm doing a divided by y to it. And we haven't seen this before. All of our arithmetic before has started with a letter and then done something where we modify it with a number. We started with a letter, we adjust it with a number, so we can unadjust it with the same number backwards. This is different. I'm starting with a number, I'm adjusting it with a letter. Everyone see the issue?
By the answer?
So if I'm starting with 30 and I do a divided by y, how would I get back to my plain 30?
You're going to divide both sides by 30. Or 3, I mean.
Divide by both sides by 3. I can try that. Let's see what happens. Actually, let me grab this whole screen in case that's helpful before I write on it more. Okay, so if I divide both sides by 3, 30 divided by 3 is 10. 3 divided by 3 is 1. So far, so good. I can still see that 10 works, but I'm sort of in the same boat. Does that make sense? I'm starting with a number and then doing things to it that involve a letter, and I don't like that. That's not what I'm used to.
You got to put the 10 over on the other side of the equal sign.
So what I actually want to do is the same thinking as before. Here's what I start with. And then here's how I adjusted it. So then we have to undo the adjusts. So we're going to do the same thing. We start it with 30. We adjusted it with a divided by y. So how do I undo that?
Times
Times y.
times y.
Because the divided by y was what I fiddled with. And that gets my 30 all by itself. Now, when I look at this, I'm happy. I have y times a number is another number. That's what I've been doing all day. Remember I said that the fact I could go both directions will be a tool? So here we are. We came to this thing by saying, let's start at 3 and adjust it with times y. But I can equally well think about it as I'm starting with y and adjusting it with times 3. So my opposite is going to be divided by 3. And I finally get the 10 that we knew from the beginning I was eventually going to get. So this is remarkable because I didn't start with y. I started with the 3 and did a times y to it. But in this row, I can treat it as if I started with y because multiplication doesn't care. So this is going to be sort of your Rosetta Stone page of your notes, that when we get to these two-step equations, why do we have them? Because instead of starting with a letter, we started with a number. And we were using division where that actually matters. So what do? We undo the letter adjustment first, which actually moves the letter to the other side. And then we do things the way we're used to. So that's too much in your head right now. Let's do a whole bunch of example problems. Okay, I am starting with 20. I am adjusting it with a divided by W, which I don't like. So I will unadjust it with the times W. That gets the 20 by itself. And it turns my equation into a number is a number times a letter. So what's my next step going to be?
Divide W or 0.4.
And you could double check, is 20 divided by 50.4? Yes, it all works out. Does this look less scary now that I haven't filled up the board so ridiculously?
Yeah, but it still looks a little confusing until you do it a couple of times.
Yes. So this isn't terribly important. This is like maybe one problem on your final exam and so on. The reason we're showing this to you is a few things. First of all, if you're going on to Math 60, if your instructor does a good job, then he or she will on the board use colors or something to make it very clear this pattern of action step, what's the consequence? Action step, what's the consequence? Does that make sense?
Yeah.
By the end of the term, everything will be in the same color. Because in real life, people don't have time to stop using a pencil and keep doing things like this nicely. So part of a good Math 60 instructor's job is to wean you of the color coding, where the action steps get their own color from the consequences. And you should know this, because if someone doesn't do it right and starts out all the same color, then you can say, excuse me, instructor, can you put your action steps in a different color, at least for the first few weeks of class? That really helps my brain see what's happening. But for Math 20, it's not my job to wean you of the color coding. I'm always going to have the actions in a different color. It's also true that we don't want you to be surprised. You're used to thinking something attached to a letter is something else. I know how to solve that. And when it's multiplying or adding, yes, whether you attach it in front or behind the letter, you can solve it. But with division, it matters which order. W divided by 20 and 20 divided by W are entirely different things. One of them is a one-step problem, the other is a two-step problem. Right? Something letter divided by something you can undo real quick. But something divided by letter is 2 steps. So I don't want you to get trapped and get surprised that, oh, I thought I knew how to do these. Why isn't it working? It's because they've switched the order on you and put the letter after the divided by instead of before. No one in Math 20 really cares if you can solve this problem or not. They just want you to not get stuck and think it's W divided by 20 and then panic and say, oh, I'm stupid, I can't do these problems. It's a different problem. Okay, let's look at these two. Are these 1-step problems or 2-step problems?
1 step.
And how do you know that?
Because the letter comes first.
The letter comes first both times. By the way, subtracting also makes 2 steps, because just like dividing, the order matters. Multiplying and adding, the order doesn't matter. Should I do either of these, or are you very good at 1-step problems?
I think I'm very good at it.
Okay, I will do it very quick, just for the people at home who are watching video to have the answers, but I'm not going to talk as much as usual as I go. So again, however you write these, keep your letters lined up, keep your equal signs lined up. Don't interrupt the flow of things with a bunch of arithmetic. Put that off to the side somewhere. And if your Math 60 teacher isn't writing things on the board in such a neat, organized way, then scold the person and say, I'm just starting Math 60.
Wait, so why on the first one did we do 1/8 times 1/4, but then on the second one it's 1/8?
Because I'm not,
Oh,
I'm dividing by 4/1.
okay,
And how do I divide by 4/1? I flip it and multiply.
okay, I get it.
Good question. Anything else where I should talk more because I didn't talk during it? Okay, how about, oops. Holler if you need the previous slide. I don't want to rush anyone. Anyone need more time here? Okay, one-step or two-step equations.
First one's 1 step, second one's 2 step.
Correct. And that's the big lesson for the two-step thing. As long as you can identify them, feel ready for Math 60. It's not your job to learn how to solve the two steps in Math 20. You probably can, because again, the process isn't that bad, but the main job is just what we already did. Okay, questions about any of what we've done?
No, it's just going to take some time to become comfortable doing it.
If you actually become comfortable with this, you're like a week and a half into Math 60. So great. As a reminder, your main reason I'm showing you this is for subtraction. If the letter comes first or second matters a lot, and I just want it in your head how much it matters. This one is the only one-step thing we really care about. If it makes you not afraid of Math 60, that's a good side effect, because again, this isn't that bad. Everyone ready for something more pleasant?
Yep.
Okay, lots of videos about these. These are all one step, because again, that's all the thing that's official in Math 20. Now I get to make you happy, because there are tremendous numbers of Math 20 students that just love cross multiplying. As I mentioned last time when I was doing a quick overview at the end of class, we save cross multiplying for the end, partly so that people don't try using it during the first 6 weeks of the term when there's no need to use it. Some people like this so much, they just cross multiply whenever they can. So we're on page 381. It's actually coincidentally section 5.3 of both books. And our first definition, let me get that on one line. I'm going to start our new Jamboard actually, rather than have one slide of the next topic. That would be awkward. So a proportion is an equation of the format ratio equals ratio. So earlier in class, we had 2.2 pounds goes with 57 grams, and we found out that that was the same as, actually let me make this all match because I know what's going to happen later. 143 dollars to 1 ounce is $11.14 for 8 ounces. So that's a great proportion. It has a ratio. It's equal to another ratio. If it costs this much money for an ounce, if I wanted to buy an 8-ounce package, I'd have to spend that much. We also had that wonderful segue that for, where was it? Oh, I don't know. Sometime we talked about how when we do things with rates, we do different things with rates than we do with plain numbers. So now we're finally getting to something else we do with rates. Other than take one rate and change it into something that's equivalent, then what else could we possibly do with rates? Well, we're going to do this cross-multiplying thing. So notice before I move on that if it's anything other than ratio equals ratio, it's not a proportion. So if I put like a +1 on one side or something, that's not a proportion anymore. It has too much stuff, too many parts. So you've probably seen something like 2/4. Maybe it's the same as 5/10. And notice I'm writing a question mark over my equal sign. I'm saying the point of this is I'm not sure if it's true. Is it true or not? And this one is purposefully easy. I hope we can all just look at it and say it's a half and it's a half. So of course they're the same. But you've probably been taught this bizarre thing where one way, if you can't just see it, to check if a proportion is true, if the ratio really is equal to the other ratio, is I'm going to take one diagonal and multiply it. Let me see if I can draw that better. And then I take my other diagonal and multiply it. And if these numbers are equal, then my original proportion is also equal.
Will that work all the time?
It does. Is there anyone that's never seen this before?
I've never seen that.
Okay. So what's happening? Why does this always work? So here is a picture. Actually, I can get both of these on the screen. In the first example, it works out. In the second example, it doesn't. 6 times 9 is not the same as 8 times 7. So this was true, and this is false, right? Or if I don't like true and false, then I can say that this one was equal, and this one is not equal. I really, to be writing these correctly, should have a question mark there. I'm not sure why wherever I copied this from doesn't have it. So why does this work? Why can I multiply diagonals to check if the proportion is equal?
Does it have anything to do with back when we were like talking about the ratio thing and we had to put the label opposite so that we could cross it out?
Yes and no.
Other than that, I have no idea.
So it is true that I want to take the 2/4 and do something to it. And I want to take the 5/10 and do something to it with legitimate fraction arithmetic.
You're just simplifying them.
Or I'm unreducing them is what I'm actually doing.
Simplify or find the common denominator.
Yeah. Let's pretend that we are little kids just learning about common denominators. And somebody said are 2/4 and 5/10 equal. And we're so new to fractions that we can't just look at them and say they're both equal to a half, so of course they're equal. Then we might think, I can't compare fourths and tenths. Those are too different. But I can take the 10 from here and make it a common denominator. And I can take the 4 from here and make it a common denominator. And if I do something to the bottom, I have to do it to the top. Now I have 20/40ths and 20/40ths. And no matter how new I am to fractions, I can say that yes, those two are the same. Similarly, for the bottom problem, if I have 6/7 and 8/9, are those the same? Well, I can't compare 7 and 9ths if I'm very new to fractions, but I know how to make them the same. I can say that let's times 9, so that whatever that is, it's going to match. If I do a times 7 here, they're both 7 times 9. Even if I don't know right away, that's 56. If I do something to the
63.
bottom, I have to do it to the top. So in this case, I get 54. Yeah, I'm sorry, I said 56. 9 times 7 is 63. And I'm reading on the other side instead of thinking clearly. Okay. So this cross multiplying game we're doing is exactly the same as brute forcing the common denominators. Is this the least common denominator? I don't care. I'm going to multiply each denominator by the other. Remember that from weeks ago when we were adding fractions? But this is too much writing. Nobody cares in the first problem that we're at 40ths. Because whatever this number is, it's going to be the same. That's why we did the brute force denominator trick of multiply each denominator by the other. So of course the denominators are the same. We're forcing them to be the same. All we're wondering is, do the numerators happen to match? Similarly, for the second problem, no one cares about 63. Of course, if we multiply the two denominators by each other, they're going to be the same. I don't care that 9 times 7 is 63. I'm just wondering, do the numerators match? So that's what this is. These are the numerators of a brute force common denominator problem. And you don't really care about that. You just want to do the cross multiply game. Make the diagonal, check if it's the same. But you are smart people and deserve to know why this works. And now you can see that it's just leaving out the denominators from finding common denominators.
Well, I appreciated learning that because I never saw that before like that.
Yeah. Okay, any questions about these two slides? So I would love to go on a little more deeply, but we're out of time. So I'm going to do one more problem because this, by the way, is stupid. No one will ever give you two fractions in real life and say, by the way, are they the same? Right? When does that happen? But for scaling things, it happens all the time in real life that we have one of the four parts is a letter. And this is a totally different game. I am not checking if things are equal anymore. Instead, I am being strong and burly and saying there must be some letter, some number that plugs into the y that will work. Whatever it is, I am going to find it. So it's not a double checking. Instead, it's a force this to work. Find the number that makes it work. But the process is exactly the same. Let me get my colors right. I did blue with that diagonal. So in one diagonal, I have a y times a 1.2. On the second diagonal, I have a 96 times a 1.3. By the way, does it matter what order I put these things?
Not in multiplication.
No, it's always going to be multiplying, and it never matters for multiplying. Also, does it matter if I put the blue on the left or the right?
No.
No, two things are equal. It doesn't matter which one I write on the left or the right. So no matter how the setup is, I will always have the freedom, because my brain likes it, to pick the one with the y and put it on the left side of the equal sign. And I will always have the freedom to put the letter first. So all this dangerous stuff we saw about what happens if the letter is second, when there's subtraction or division, we can ignore this. This is why we don't care about two steps in Math 20, other than the heads up about them. Because we will only be multiplying, and we will always have the freedom to put the letter first. Okay, so now I'm back to the one-step ones. Y times 1.2. Now I don't know what 96 times 1.3 is, but my calculator does.
124.8.
8. Oh, okay. Am I dividing by 1.2? Am I dividing by 124.8? Are we paying attention earlier?
5 by 1.2.
So this isn't enough example problem, and I purposefully picked one with decimals to be scary. But this is what we will do a whole lot when I see you on Wednesday. So we're taking the two tools that we talked about before, the one-step equations, because from here down, it's the one-step equations, and the cross multiplying, and we're using them to solve this. And this is tremendously useful in real life. So we'll talk about that more later. So that's your heads up of what's happening, and we're a minute late. So thank you for your patience.
Thanks for taking the time to explain that earlier.
No problem, it's my job.
Thanks, David.
Thank you. Have a good day, everyone.
You too. So there is a study session at noon. If somebody wants to come back and do work together, we can. Otherwise, see you Wednesday or Tuesday study session.